Welcome to the Software Engineering channel on YouTube. Today we're going to go over C++ syntax and data types. To start with, as you saw in the previous examples, there are a couple different types of comments. There are inline comments, as you can see here. Draw it here, where everything after the double forward slash will be treated as a comment until the end of the line. What this allows you to do is what you can see here, where you can state what you're doing on a specific line. You can also comment on an entire line by putting it at the beginning and document what's going on in the following line, for example. And then you have block comments. Block comments can be used for a portion of a line, for a whole line, for multiple lines. It starts with a forward slash and a star, and it will continue until you have a star and another forward slash. This means that if you start the forward slash and star, the rest of the file will be commented out until you close it. So you need to make sure that you close it appropriately. So, when should we use comments? Well, ideally, your source code should be what's called self-documenting, meaning I should be able to look at your source code and understand, based off of how you named your variables and how you named your functions, what's going on. Comments should be used to clarify something that is not obvious when I look at the code. You had to do something special because of, let's say, an optimization. So you had to use something that's not common, or you had to do call a different function or change the order, or you had to use a special arithmetic because it's more efficient. Things like that come up. A lot of them will come up when you're doing performance optimizations, but when you get into those kind of situations, you want to make sure that you comment, here, this is what's going on, this is what it's doing, and here's why we had to use this method instead of a normal method. What you don't want to do is leave blocks of source code commented out. We have source control systems like GitHub or Subversion, things like that. If you make a mistake, you want to get rid of a block of code, get rid of it, check it in the source control. The history will be maintained in the source control. Don't leave blocks of commented code in what you're working on. And also, don't leave comments that just explain what the operation is doing. For example, don't leave a comment that here says, I'm creating a constant double named pi, and I'm initializing it to the value of pi. I can see that based off of what's actually going on here. I don't need you to tell me again what's actually going on. So even this comment here where it says the need a value of pi for calculations, I probably would be better served to explain what calculations will be used. So for example, I need a value of pi because we'll be doing a lot of trigonometry or a lot of calculations dealing with circles, and so we need a value of pi to deal with that. Something along those lines. C++ has a bunch of data types built in. These are called primitive data types. They're built in the compiler, and they're reserved keywords as part of the language. So you can't name a variable bool, for example. The compiler will scream at you. So going through these real quickly, the primitive data types are Boolean, as we just mentioned. That's a value of true or false, or more specifically, it's a value of false and not false. Because anything that's not 0 will be considered true. Then you have a bunch of different integer data types, and these can also be signed or unsigned. The default is signed. The smallest integer is called char. It's actually can be used to store ASCII characters and for text strings as well. On most systems, it will have 8 bits, which is a single byte. The next smallest one is a short, which is typically 16 bits or 2 bytes. Then you have int and long, which on most systems are the same size, and most of them are considered 32 bits. And then long is a 64-bit. And some of these sizes will depend on the hardware you're using, the compiler you're using, and the operating system that you're running. But they all have standards for those platforms. But on typical systems, these are what the sizes will be. And then the size that you'll use for these various types will largely depend on what your application is trying to do and how big you need these numbers to be. If the maximum number for a given application is going to be 200, then using a 64-bit integer is going to waste a lot of bits. You're never going to end up using more than the first several bits. Conversely, if you need a number in the billions, you can't use an 8-bit integer. It's just not going to work. You'll get what's called an overflow error, where it tries to write outside of memory space and can cause a whole bunch of problems. Then you have floating point numbers. You have float, double, and long double. Floats are typically about 32 bits, and doubles are typically 64 bits. Long doubles are typically 128 bits, though they may only actually use 80 bits, depending on the system. The more bits, the more precise the number can be. Float typically has a precision of about 7 decimal digits, a double around 15 decimal digits, and a long double around 33 decimal digits. Void is a special type that means there is no type. This is most often used for the return value of functions that don't require a return value, because all functions are required to have a return value of something. So if you need to have a function that doesn't actually have a return value, you use void as the return value. However, you will also see it used for backwards compatibility with C, the language C, where you can use it as a pointer for any other type. So you can cast any pointer type to a void pointer and, shove it around and use it accordingly. You typically do not want to do that in C++. So the main reason you would do that is if you are dealing with backwards compatibility with something that was written in C. So next we have derived types. These are types that the language supports baseline, but they're not actually user-defined. These are things like functions, pointers, references, and arrays. Functions perform operations. You can also create pointers to functions and pass them as parameter to other functions, which is something we will see much later on when we get to algorithms. Pointers are variables that hold an address or a memory location to an actual type. Note that a pointer can refer to null, meaning it does not yet hold a valid address. Conversely, a reference is an alias to an existing variable. Once the reference is initialized, it cannot be changed to refer to a different variable. So a reference can never be null. It always has to refer to something that actually exists. And then finally, arrays are continuous groups of data types. You can have arrays of all sorts of different data types, whether they're primitive or user-defined. User-defined data types are the types the programmer creates to fill the needs of an application he or she is creating. Classes and structs are the most common. They are almost identical in C++, the main difference between the two being the default protection mechanism, which we'll cover later when we get into classes. A union is a very special type where it can be one of many different types inside, and the actual size of the union is going to be the largest member of the union. So you could have a union that has an integer, has a double, has a string, and maybe has a pointer, and it will actually, the size of the union will be the size of the string, because that's the largest of those, and the value of the union will be whatever is actually initialized. So only one of those values can actually have a value at any given time. Unions are not all that type safe. They're mainly there as backwards compatibility for C. There is a new type in the C++ standard called variant that addresses the type safety issues of unions. We'll cover that a little bit more when we get into the C++ standard library. Enumerations are a user-defined type where the value is limited to a specific range. So let's say you wanted to define a list of colors. You would give them numerical values, and the enumeration, anything that was declared as the enumeration type, would only be able to have those specific values. A typedef is a way to alias another type so that you can refer to it by a different name. This is useful when you want to make your code more readable without having to add comments everywhere state why you're using a certain type. So for example, if you want to have a zip code and you want it to be a string, you can typedef zip code as a new type and as an alias to string. So anytime you use zip code as a type, it actually will create a string, but you can actually see what you're meaning to do with it. And it helps improve your readability. In some cases, it can actually make it so that you don't have to type out a very long type. If you wanted to create a function pointer, for example, typing out the function pointer syntax every time you needed to declare it would be rather tedious. Using a type def where you declare it as a function pointer will speed things along and make it more readable. C++ has a bunch of different operators, and they all have a specific precedence. So here we have this table. It's actually going to continue on to the next slide that describes the precedence and what the operators actually do. So scope resolution is the highest precedence. This operator tells the compiler where the variable or the function is located. Recall from the previous examples that we used that there was the std::. So that's indicating that what we were looking at was in the standard library. You can also create your own namespaces where you would want to use your namespace : instead of standard : in addition, it can also the : can be used to access static members of a class or enumeration types. So in the next level, we have member selection, which is how you tell the compiler what variable or function within a class or struct that you want to access. You have postfix, increment, and decrement. And note that in C++, postfix, increment, and decrement, and prefix, increment, and decrement are different. Postfix will increment the variable and then return the previous variable. The prefix version, which we'll talk about at the next level, will return the new value. So if you say you had an integer I, a prefix increment will take I. Let's assume it was initialized to 5. If I increment it, the return value of after that increment is going to be 6. For the postfix, if it was still at 5, when we called the postfix increment, the return value is actually going to be 5, even though the new value for I would be 6. And that's a subtlety that doesn't come up very often, but can catch people off guard if they're not aware of it. In the third row, we have size of, which returns the size in bytes of a variable type. You have the prefix, increment, and decrement that we just talked about. You have bitwise not, which basically flips the bit configuration of the input. So if a bit was 1, it would change it to 0. If it was 0, it would change to 1. You have logical not, which flips the logical value of the input. So if it was true, it would become false. If it was false, it would become true. You have unary plus and minus. So unary plus doesn't really do much except returns the arithmetic value that it already was. Unary minus negates the arithmetic value. So those only are useful for numbers. The address of operator, which returns the address of the operand. So if you want to figure out where, or you want to get the address of a variable or even a function, you can get that. Dereferencing, which actually takes the address and goes to that spot. It returns the object that the pointer is pointing to. Memory allocation and deallocation, that's all the new array, delete array. Those get into allocation and deallocation of dynamic memory. We'll discuss that in a different video later when we get to memory types. And then you have typecasting. And this is specifically the C-style typecasting, where you're trying to convert an operator of type A to type B, assuming they're compatible. The fourth level of precedence, we have pointer dereferencing. The fifth and sixth are the arithmetic operations. They follow the standard arithmetic principles where you have multiplication, division before addition and subtraction. Seventh level, you have bitwise shifting. This is something you won't run into much at the higher level, but it allows you to shift bits to the left or right. So if you have a number, let's say it's initialized to 1, if you shift it over to the left, then you're making it now 2. You shift it again, it's going to be 4. You shift it again, it's going to be 8, etc. And then the 8th and 9th levels are inequalities. Less than, equal, greater than, equal, equal, and not equal. Those are useful for conditional checks. So the 10th, 11th, and 12th are all bitwise operations. For bitwise AND takes all the ones from both operands. Bitwise exclusive OR takes all the bits that are different between both operands. And bitwise OR takes all the ones. So the difference between OR and AND, and it's going to require that both operands have a 1, or is going to take either of them. So if either of the operands have a 1, the resulting output is going to be a 1. And then the 13th and 14th levels, we have the logical and logical or. Same kind of thing, but for true and false. So some standard truth tables. The 15th, which is a ternary operator, this is a shorthand for an if true, then A, otherwise B statement. So those of you who are familiar with, say, Excel, the if function, this is a way of writing that. Instead of having to write if and then a block, else another block, you can put it in a simple statement for simple operations. The 16th level is assignment values, and that's how you get new values into a variable. And then finally, we have the comma operator, which is the lowest precedent operator, and it is used to separate two or more expressions. You will not see it used very often, but it does come up from time to time in for loops in particular. Next, we're going to cover C++ type conversion. As I mentioned, the C-style typecasting in the precedence discussion, this is how you do that. Specifically, this right, oops, get my pen back. This right here, where I have a type and I'm either putting the parentheses around the variable or around the type. I typically will put it around the type. And what it's doing is it's saying, hey, I know this was declared as a double, but I actually wanted to treat it as an int, so please convert it for me. This will whatever you're converting and explicitly convert it, assuming they're compatible. So the result for int I here will actually be just 5 because it will truncate the decimal place. C++ has 4 different types of cast that it uses to replace this. The problem with this type of casting with just the parentheses is you don't know which cast you're actually trying to do. So trying to sort through what cast is going on and trying to find where a certain cast is happening can get tricky when you're debugging. So C++ has safer casts that you should be using. Dynamic cast can only be used to convert pointers to polymorphic classes. This will be covered in a topic much later on. You won't have to worry about it very often. There is a overhead with this cast because it's doing some runtime checks to ensure that the types are compatible. A static cast is what you would use most of the time. It performs an explicit type conversion, very similar to the C-style casting we just saw up there. There are compile time checks to ensure that the types are compatible, but there's no runtime check. Reinterpret cast is the most dangerous of these. It'll convert any type to any other type, which can lead to unsafe conversions. You want to use this with a large amount of caution. And finally, const cast is used to manipulate the constants of an operand. So if you want to add or remove a constant qualifier, that is the casting you would use. And speaking of constants, the const keyword declares a function or variable as constant. And then there's a constant expression keyword that allows a function-like declaration of constants. These are optimized at compile time. The best practices for using these keywords is variables that should not change should be declared as constant, and member functions that do not change the object state should also be declared as const. In addition, constant expressions, let's say you have a function that calculates pi, and it's going to do that, it's not all the time. You can declare that as a constant expression. The compiler will run that. It'll basically treat it as a constant from then on. So when it goes runtime, there is no overhead, it's already calculated. In C++, you must declare a variable before it can be used. This is different from languages like Python, where you can just declare and use it anytime you want. You must declare it before it can be used. In addition, you should initialize a variable before you try and use it to ensure that it's in a valid state. This for integers, for example, you should either give them an initial default value of, say, 0, or give them an initial value when you create them. Assignment can happen at any point afterwards, but the reason that you want to make sure they are initialized, if at any point after the declaration, if it's not initialized, somebody tries to read the value that was there, you're going to end up with junk. So you could end up with whatever was at that memory location previously, and now you just have some random garbage as your value, which you don't want to use. So we've already been exposed to some of these preprocessor directives. The include one is one of the most common. Other common ones you'll see are if def, if not def, else if, end if, define, undefined, pragma. These all do various things. Define obviously defines some value at the preprocessor level that you want to hold on to. Undefined undefines that. The conditions obviously should be self-explanatory, and pragma allows you to turn certain things on and off. So let's say there's a warning for unused variables that you don't want to see because you have unused variables and they get used eventually, but the compiler just doesn't see it. You can turn that warning off. Some more uncommon directives are the line directive and the error directive. This allows you to specify the line you're on so that you can do things like state, you have an error at this particular location, and it takes you right to the file that you were concerned with. You can also provide your own custom errors when it's compiling using the error directive. And finally, the last thing we're going to look at is namespaces. As we have already been exposed to the standard namespace name, which is std : this is how you would declare your own namespace. You use the keyword namespace, and then you give it a name. This name must be unique. With the exception, you can have anonymous namespaces where you just have no name at all, but you cannot have two namespaces that have the same name. Inside this namespace, all of your classes, variables, functions are unique themselves. So you can have a my namespace 2 that has another class that's my class, and they would not conflict because they're in two different namespaces. With that said, if you use the using directive and bring both my namespace and my namespace 2 into the global namespace, you would end up with a naming conflict because you would have two my classes, and you would need to specify which one you were trying to use whenever you tried to use it. Now, with that, we're going to jump to a couple of examples in the slideshow. And here, I've already entered the first example just to save some typing time. Here, again, we're using the IOStream library. We have our main entry point. Here, I'm showing you how you can using namespace standard so that you don't have to put std : Note that I used it in the smallest scope I could. But that allows me, if you recall from the previous examples, we had std : cout. Here I can just type cout and endl. So here I'm just creating a program that is going to give me all of the sizes of all the primitive types that we've already talked about. Right, no compiler errors, so now I can run my program. And you'll see that we end up with what we'd expect. Note that the bool is actually a full byte, even though it's treated as a bit. Everything else is what you would expect. Char and unsigned char are both 1 byte, short and unsigned short 2 bytes, int 4 bytes. Here in this, because I'm actually on a 64-bit machine, the size of long and long are both 8 bytes. That you have to be very careful with that to make sure that if you're using int and long, that you're using the one that you actually expect, the size that you expect there. And then we have float double, long double, and the size of a standard pointer, which would be 8 bytes, which also happens to be the size of a long here. The other example, and again, I've already entered it just to save some time. I've declared a namespace. I'm going to call it my math. Inside of it, I declared a constant expression to demonstrate how you could do this. You could declare pi a couple different ways. I just did this so that as a demonstration. And this is a approximation of pi. And then I have two functions. One is calculate area, the other is calculate perimeter. So again, here I have the same thing with using a namespace standard. I've declared a radius here, and I notice that I've also initialized it to 0. And then I'm prompting the user to enter the radius. So they're going to enter the radius. That will assign a new value to radius. At that point, now you can see me, I'm calling the myMath namespace, and I want to call the calculate area and calculate perimeter functions, and those will return doubles. So you will see the actual output from those. So let's go. Alright, so here you can see the program running. Let's pick a radius of the circle. Let's pick 4. And here you would see that it's using, obviously, the approximation from pi. This function actually gets compiled into a constant instead of actually running this line of code to do the calculation at runtime. It actually is done at compile time. And then these functions actually get called. And because it's using this approximation, it's not going to be terribly exact, but it's close enough for our demonstration here. And with that, we will end today, and we'll see you in the next video.